In this video, we're going to look at calculating centers of mass and moments of inertia in both 2 and 3 dimensions. We're going to start with a warm-up that we would have seen in our Calculus 2 class. So in the warm-up, it says, draw the region, then compute the center of mass, x bar, y bar. Use symmetry to help locate the center of mass whenever possible. And recall from Calculus 2, the center of the mass of a lamina, which is m is equal to rho, from a to b of f of x minus g of x, where f of x is the upper function, g of x is the lower, or if it's orientated the other way, f of x is the rightmost and g of x is the leftmost function. Where our m of x, my moment in respect to x, is rho from a to b of 1/2 f of x squared minus g of x dx, and my m of y is rho of from a to b of x f of x minus g of x dx. The center of mass, of course, is x bar y bar, which is equal to the moment with respect to y over m and the moment with respect to x over m for the x bar, y bar, respectively. So we have this region that is bounded by this shape, which is x squared over 4 plus y squared over 9. Well, we know that that is an ellipse. In particular, since we want y being 0 is the bound, we're only going to take the top part of the ellipse. It's going to go 2 in each direction in the x, and it's going to go 3 in each direction in the y, but I only want that part of it. Now, we know that the center of mass is going to be somewhere along this y-axis because that's the halfway mark for our x. And so we know that our x bar will be 0. So we're going to use the fact that we have symmetry, we have x bar is equal to 0. What I need to do, though, is I need to find my mass, and I also need to find my m of x. So I'm going to find my mass. And again, this is something we would have seen in Calculus 2. So I would integrate from 0 to 2. And I have 2 of these, so basically I'm just doing 1/2 of this integration. Because of symmetry, I'm going to just multiply that by 2. And so then from 0 to 2 of my rho, which is, we actually don't know, so I'm just going to use rho. And then my upper function, because I'm doing this with respect to x, is going to just be, well, we have to spend some quality time solving for my y here. I need to take this and solve for y. So I have y squared is equal to 9, so I have to multiply both sides by 9, and I have x minus x squared over 4. So y is going to be equal to the square root of 9, 1 minus x squared over 4. And I'm going to go ahead and factor a 4 out. So I have the square root of 9 divided by 4, and then 4 minus x squared. And that's just so I don't have to worry about the fractions. And I can now take the square root of 9 and the square root of 4. So I end up with 3 over 4. And then I have my upper function. Well, my upper function is the square root of 4 minus x squared, and then minus my lower function. My lower function is 0, so minus 0, so in other words, dx. All right, so let's go ahead and do the integration, and when we end up with the integration, we're going to have 3 rho and pi. That's just doing our regular integrations, and however we normally do that. Now I have to find my moment with respect to x, so m of x. And this is going to be 1/2 the integration of from a to b, which is -2 to 2. So -2 to 2, negative 2, and I wrote 1/2. So -2 to 2, I got 1/2 on the brain. -2 to 2 of my rho. And again, I'm going to have my upper function and my lower function. Well, my upper function is 4 minus x squared still, and it's squared. And then minus my lower function, which is 0, so we don't have to worry about that part. And then dx. And then what I end up having for this is I'm going to have 12 rho. Now, notice we make the assumption that our density is constant throughout the lamina. So it doesn't really matter what rho is. My y bar is going to be equal to my moment with respect to x over my mass. So it's going to be 12 rho over 3 rho pi. And so I finally just get 4 over pi. So this is a nice refresher from our calculus too. So my center of mass is going to be x bar comma y bar, which is going to be 0 and 4 over pi. Nice refresher. Now let's take this to the next step. Suppose we have this region where I have my density, which is going to be a function of x and y. So now we don't make the assumption that our density is constant throughout the shape. So that's going to change things a little bit. And we're going to be looking at this lamina shape, and we don't know what it looks like, but we do know that mass is going to be equal to the integration. And the way that we're going to approach this is by taking our lamina and chopping them up in little bitty pieces and doing Riemann sums, which gives us this. So my mass is going to give us now my rho as a function of x and y over the region, so the region's whatever the region ends up being, and then dA. Similarly, when I do my moments, I'm going to have y rho of xy dA, and my moment with respect to y is going to be x rho, my rho as a function of x and y. So then I can find my two x bar and y bars, my centers of mass, and this is in 2 space. We're going to do 3 space in a minute. If we look back at our example here that we started out with, this is what it would look like then. I would have from 0 to 2 of for my dx, and my y went from 0 to 3 over 2, the square root of 4 minus x squared. Rho being a constant, we don't know what it is, so we're just going to leave it as rho. Then my moments would be this, which is actually kind of nicer, at least to begin with. The integration isn't going to be that different, but that's what we end up with. So let's take a look at this one. And I'm asked to find the mass of the lamina. I'm not asked to necessarily find the center of mass, but I do know where the center of mass is by symmetry. I know it's going to be right there, right? It's going to be right here by the symmetry. Assuming, of course, our density is the same throughout. If my density is not the same throughout, then my center of mass will not be there at that place. It's going to be dependent on where my heaviest piece of my lamina is. So that's not what they're asking us to do, though. They're just asking us to find the mass. So my mass is going to be equal to my integration over my region R of my function rho of x, y, dA. So I'm going to do this with symmetry, and I'm going to have my x part first. Oh, my rho is constant. Oh, so I could tell you the center of mass is right there. Oh, you don't care. I care. I think it's kind of cool. Anyways, so I'm going to just work with one side so that I can do this with symmetry. Symmetry, I can do this without symmetry, but symmetry is going to be much easier. So I have to figure out what my limits of integration are. My x is real easy. X is going to integrate between 0 and 1, so 0 to 1. My y is going to integrate starting with, this is going to constrain the bottom part of my y, which happens to be the line y equals x. So this is going to be my bottom, my lower index for my limits. This line is going to contain the top part, and this line is the line y is equal to negative x plus 2. I don't read it there. So this will be negative x plus 2. Now my rho is nice, it's 1. And then I'm going to do dy first. and then dx, because my x is dependent on my y. Okay, so let's do the integration, this part right here first. So this is going to be y evaluated from x, and then negative x plus 2, which is going to give me negative x plus 2 minus an x, so negative 2x plus 2. So now I'm going to integrate from 0 to 1 of this negative x plus 2 dx, which is actually a really nice integration. It ends up becoming negative x squared plus 2x. And don't forget, I should have this 2 out front because of symmetry. I still have this 2 out front. Dropped it. I talked about it. I just dropped it, 0 to 1. And so when I get totally done, my answer is 2, and it's whatever my units of mass are. Okay, let's take a look at my next example here. When we start setting up our limits of integration, it's not too bad, right? So we think, okay, we'll start from 0, and, well, if we take this and solve for x, I'm going to get x is equal to positive and negative 1/3, but you can see it's just 1/3 there. So that's cool, from 0 to 1/3. Even the y doesn't look that bad. Y is going to go from 0 to this function, and so I'm going to solve this function in terms of y. So I've got y is equal to the square root of 1 minus 9x squared. So square root of 1 minus 9x squared. You're thinking, okay, well, that's not too bad. Well, here's the thing. I have the square root of 9x squared plus y squared dy dx. And that's where it's not nice. So it just isn't nice. What I'm going to do then, since this isn't terribly nice in Cartesian, is I'm going to go into polar. So using the fact that we have r is equal to, x is equal to r cosine theta all day long, x is equal to r cosine theta all day long, y is equal to r sine theta all day long. We also have the fact that r squared is equal to x squared plus y squared. And so I'm going to convert this all into polar because it actually is going to be easier. Now the setup is not fun, but when we go to integrate it, it's actually much easier. So I need to convert the 9x squared plus y squared is equal to 1 into its equivalent polar. Replacing everywhere I see x with r cosine. So I have 9r squared cosine squared theta plus r squared sine squared theta is equal to 1. So what I have then is I'm going to factor out an r squared, and I'm going to have 9 cosine squared theta plus sine squared theta is equal to 1. That means r squared is equal to 1 over 9 cosine squared theta plus sine squared theta. That means r is equal to, and I'm only going to take the positive, right? So it's going to be 1 over the square root of 9 cosine squared theta plus sine squared theta. So that's going to be my upper bound for r. Now, my angle of rotation is between 0 and pi halves. So I'm going to integrate last my theta, so from 0 to pi halves. My r is going to go from 0 to 1 over the square root of 9 cosine squared theta, the sine plus the sine squared theta. Now, that one seems awful, but it's not too bad. Don't forget, every time I do polar, I need an r, dr, d theta. I'll do theta last. So d theta and I need to convert this. And this becomes, fortuitously, 9r squared cosine squared theta plus r squared sine squared theta d theta, which is going to give me an r, 9 cosine squared theta plus sine squared theta. And I will have a d theta. I'm just not ready for it. There. Okay, so this brings in an r, the square root of 9 cosine. I don't know why I want to do sine there. It should be cosine. So cosine squared theta plus sine squared theta. Now, let's do this integration right here. Okay, so this is going to integrate this. It's going to be the square root of 9 cosine squared theta plus the sine squared theta, r raised to the third divided by 3 from 0 to 1 over the square root of 9 cosine squared theta plus sine squared theta. So this is going to give me 1/3 the square root of 9 cosine squared theta plus the sine squared theta multiplied by 1 over the square root of 9 cosine squared theta plus sine squared theta raised to the third power. So what ends up happening here is that this cancels with one of these. So in other words, I'm going to have 1/3 1 over 9 cosine squared theta plus sine squared theta. And you're thinking, wow, that's still not fun. Well, actually, it's not that bad. So we are now at 0 to pi over 2. I have this 1/3, so I'm just going to pull that 1/3 out front. I have 1 over 9 the cosine squared theta plus the sine squared theta d theta. And this looks an awful lot like, well, if I were to divide by cosine, this looks like 1 over 9 plus the tangent squared theta, which actually looks a lot like 1, oh, and I should have a tangent up here too. So I'm dividing everything by cosine squared, so cosine squared theta. So if I then divide everything by 9, this looks a lot like 1 over 9, the cosine squared of theta, 1 plus 1/9, the tangent squared theta, which looks a lot like 1 over 1 plus u squared u prime, which is a really nice integration. So if that's what it looks like, let's go ahead and label. Let u equal 1/3 the tangent of theta. Then du is going to be 1/3 the secant squared of theta. Ew, well, look at that. Now, normally I'd change my limits of integration, but I'm going to wait. Now, so then this is equal to 1/3 the integration from 0 to pi over 2 of 1/9 the secant squared of theta over 1 plus 1/9 the tangent squared of theta d theta, which means I'm going to end up with 1/9 the arctangent. Because I know if it's in this kind of form, which is the 1 over 1 plus u squared u prime, that we know when I integrate this is the arctangent of u. So this is going to be the arctangent of 1/3 the tangent of theta evaluated between 0 and pi over 2. Now, the 1/3 isn't going to do much because, oh, and by the way, I need to write this as 1/3 and make this a 9 because I need 1/3 the secant squared, not 1/9. So that's 1/9. So this should be 1/9 there. Okay, so 1/3, the tangent. So the tangent at pi over 2 goes to infinity. 1/3 of infinity is still infinity. The arctangent of infinity is going to be pi over 2. So this is 1/9 times pi over 2. The tangent of 0 is 0 all day long. The arctangent of 0 is 0 all day long. So my final answer is pi over 18. That's the mass. This was almost near impossible to do, by the way, without going into polar. This was, and even in polar, holy moly, that's a whole lot of work to get the answer. But it was a nice refresher. Let's take a look at my next example here. Find the moments now. We want to find the moments, and we want to find the center of mass. So I'm going to approach this with respect to x first, and then I'm going to do it with respect to y. So I need to figure out how x is contained. And the reason I'm going to do that is because this is, if we think about this back and we learned integration with in 2 dimensions, it's a type 2. So I want to do it with respect to y second with respect to x first because x is going to depend on y. So I'm going to do with respect to x first. X is going to be contained between 0 and this equation. So I take this equation, which is this, and I solve for x. So x is going to be equal to negative 4y plus 10. So x is going to go between 0 and negative 4y plus 10. I have the function 3xy, that's my density function, and then it's going to be with a dx first. Y is going to vary between 0 and 2. Then I do dy. Now, I'm not going to bore you with all the boring details. I'm just going to go right to the chase. My mass, then, is going to be equal to 152 over 6. So in other words, 76 units. Now I have to find my moments with respect to x, because this is going to give me, my moment with respect to x is going to give me my y bar. And the only thing I have to do now is introduce an additional y. So it's still going to be 0 to 2. From 0 to negative 4y plus 10. I'm going to introduce another y in with my density function, so it's going to be 3xy squared, still dx, still dy. When I get done with this, I end up with 73.6. 73, I don't know why that does that sometimes, 73.6. My m of y, when I integrate this, it's going to go from 0 to 2, still from 0 to negative 4y plus 10. Now I introduce a secondary x, so it'll be 3x squared y dx dy. When I get done with this, I'm going to get 310.4. So my center of mass, which is the x bar, y bar, well, we know that x bar is going to be the m of y divided by my mass. My y bar is going to be m of x divided by my mass. And so my answer is going to be about 4.084 and 0.9684. So that's my center of mass. Now let's take a look at this one. This looks like it's going to be easier to integrate with y second, so I'm going to call this a type 2. My y is going to go from 0 to 1. So that's my y from 0 to 1. Here's my rho, so I'll need that too. My x is going to be contained between this equation right here, which is y is equal to x. That'll be my first x I see, so that's going to go from y. And then my other containment for x is going to be this line. So I'm going to solve for this line, and this line solved is going to be 3 minus y. So 3 minus y. And I actually, you know what? I'm going to do this in red. I don't know why I chose green. So y to 3 minus y of my density function, which is 2x plus y, dx first, and then dy. Again, I'm not going to bore you with all the details because you all are probably like rock stars when it comes to doing the integration, and I get 41 over 6 units of mass, whatever they may be. We don't know what they are. We're just going to say they're units of mass. Now I have to find my m sub y and my m sub x. My m sub y is going to be the integration from 0 to 1, y to 3 minus y, 2x plus y. Now because I'm doing it with respect to y, I'm going to introduce another x, dx dy. And this, when I get done, is going to give me 143 over 12. My m of x is going to be from 0 to 1, y to 3 minus y. Now I'm going to introduce another y, so it'll be y, 2x plus y, dx dy. When I get done with this, I'm going to end up with 3. So my center of mass is going to be 143 over 82 and 18 over 41. Now let's talk about the moment of inertia. Well, what the moment of inertia is, also known as the moment of mass of inertia or angular mass, or most accurately, rotational inertia. So if we have a rigid body, and what the moment of inertia is a quantity that determines the torque needed, the power needed, the force needed for a desired angular acceleration about a rotational axis. This is kind of like doing how easy is this to flip over? How much force do I need to get this to rotate about usually the center of mass? So when we're looking at the moment of inertia about the x-axis, we get this double Riemann sum, and it ends up becoming this equation. So it is y squared times my rho function of x and y dA. If I want to know the moment of inertia in the y direction, the y-axis, then I'm going to have r x squared rho xy of dA over my region R. Sometimes we need to find the moment of inertia about the origin, which is known as the polar moment of inertia. To find the polar moment of inertia, denoted as I sub O, then it's going to be both x squared plus y squared rho of xy dA. Sometimes it's convenient to write this in polar equations, and in polar equations, this would be my rho as r cosine theta, r sine theta, where I have r squared dA when I'm doing my moment of inertia around the polar. If we are in 3 dimensions, well, what changes? Well, I have the moment about the xy plane is this, but I also have a moment around the xz plane. I have a moment around the yz plane. The center of mass is still going to be divided by m. So we have the moment in the xz plane for the x bar, the xz plane, the yz plane for the x bar, the xz plane for the y bar, and the xy for the z bar. And then what changes here is if I want to end with respect to x, it'll be x squared plus z squared. The y is x squared plus z squared. And the z is x squared plus y squared. Still rho xyz dv. The moment of inertia of a particle of mass m about an axis is mr squared, where r is the distance the particle is from the x-axis, also known as the radius of gyration. So this r is the radius of gyration, and it basically tells us how far in the perpendicular distance the moment the axis of rotation of the entire mass might be concentrated. Looking at these examples, we want to find the moment of inertia, the radii of gyration about the xy axis and the origin. So I need to find my moment of inertia with respect to x. This is going to be the integration over my region of my y squared and then my rho of xy, my dA. So I have this trapezoid, I have these lines, and so my equations, if you notice, are pretty much the ones we used in our previous example up above. So my integration is still going to be from 0 to 2. This is the trapezoid from up above. From 0 to negative 4y plus 10. Now I'm going to have my y squared, and then I'm going to have a 3xy. If you remember before, we did it with respect to x first and then with respect to y. We end up with, well, I can pull the 3 all the way out from 0 to 2, of 0 to negative 4y plus 10 of xy to the third dx dy. And doing my regular integrations, I end up with 88. Now I have to do the same thing for my moment of inertia with respect to y, is again the integration from my region. This is going to be x squared rho xy dA. Surprise, surprise, my limits are still from 0 to 2, from 0 to negative 4y plus 10. Now I have x squared, 3xy dx dy. Still pulling that 3 out from 0 to 2. From 0 to negative 4y plus 10. And now this is going to be x to the third y, and then dx dy. And when I get done with this, I end up with 1560. The last thing is they're asking me for the x in terms of the origin. Well, this is just going to be the x of the moment of inertia around the x plus the moment of inertia around the y, which is just going to be 88 plus that 1560, which gives me a total of 1648. Now, to find my radii of gyration, r of x, this is going to be the square root of I of x over my mass. Well, we know the mass, because we've already done that, and that was in our previous example, was 76. So this ends up becoming the square root of my I, which is 88 in terms of the x, over the 76. My r of y is the square root of my moment of inertia in the y over that 76, which ends up being 1560, the square root, divided by 76. And last one is with respect to the origin. And so this is going to be the 1648 divided by my mass, which we know still is 76. And surprise, surprise, guess what? B is also another one we've already done. So skipping to the chase, we have I of x is going to be equal to, again, we've done this. It's from 0 to 1, y to 3 minus y squared, x, 2x plus y, dx dy, and this ends up becoming 37 over 20. My I of y from 0 to 1, from y to 3 minus y, now of x squared, 2x plus y, dx dy, which is 1387 divided by 60. My I about the origin is going to be ix plus iy, which ends up becoming 749 over 30. Because we've already done this, we already know what the mass is, because we did the math, so the radius of gyration r of x is going to be the square root of 1387 divided by 60 divided by our mass, and we found our mass from before is 41/6. So when I get done, it reduces to 111/410. My r of y is going to be the square root of 1387 divided by 60 divided by the 41 divided by 6, which gives me 1387 divided by 410. And then we have our last one, r of o, which is the square root of 749 divided by 30, 41/6, which gives us, when we finally get done, 1,498 divided by 410, and I'm okay with a decimal equivalent 4 or 5 decimals out. Now, let's do this one where we have 3 space. So we're going to consider this solid. From x is going to go from 0 to 1, y is going to go from 0 to 2, and z is going to go from 0 to 3. With this given density function, find the mass, find the moments, and find the center. The mass is going to be the integration over my region Q of my row function x, y, and z dv. So this is going to be equal to, let's do x last, from 0 to 1. And then we'll do y next from 0 to 2. And we'll do z first just because we can, from 0 to 3. Of my density function, which is the x plus y plus 1 dz dy and dx. So this is actually not a bad integration. My limits are nice. When I get totally done, I should get 15, and it's units of mass. So here's part A. Let's take a look at part B. We want to find the moments in terms of the mz, mxz, myz, and mxy. So let's just start with one of them. M with yz is going to be equal to the integration over my q. And it's going to be x rho xyz dv. So this is going to be equal to, from 0 to 1. I'll start with, actually, let me do the same colors. I'll do my x's last, from 0 to 1. I'll do my y's second, and I will do my z's first. So this ends up becoming x plus y plus 1, dz, dy, and dx. Again, this should not be any surprise. I think we've got rid of the worst stuff. That gives me 8. What I mean the worst stuff was, our last section wasn't bad, but it wasn't a whole bunch of fun either. So I'm going to do m of xz, again, the integration of q, and this time I have a multiplier of y, of my row x, y, and z dv. Starting with my x's, 0 to 1, my y's, 0 to 2. Actually, I'm not starting, it'll be my last thing. 0 to 3, and now I'm going to have a y, x plus y plus 1, of dz, dy, and dx. And when I get done here, I end up with just 17. Last one, m of, let me see, it would be zy, which is equal to the integration over q, and that'll be z of my row. No, this would be xy. last one I didn't have is xy. xy. That's why there's a z there. Rho xyz dv. The integration from 0 to 1, 0 to 2, 0 to 3 of z, x plus y plus 1, dz, dy, and dx. And my final answer on this is the first time where I didn't get a nice integer number, ends up becoming 45/2. Last part, which is part C, is we want my center of mass. We know that y bar, x bar, we'll start with x bar. X bar is going to be equal to my m of yz divided by my mass. My y bar is going to be equal to my m of xz over my mass. And my z bar is going to be equal to my m of xy over my mass. And we found our mass earlier. We found that to be 15. So my z bar is going to be 45/2 divided by 15. Make sure you reduce that. My m of y, or excuse me, my y bar is going to be the 17/15. And my m of z ends up becoming 8/15. So my center of mass for this is going to be 8/15, 17/15, and this reduces to 3/2. So that is the location of the center of mass for this particular shape with that density. Okay, so let's take a look at this last example here. The solid Q has a moment of inertia x about the xz plane given by this triple integral. Find the density and find the moment of inertia about the xy plane. Well, we know that the I of x is equal to my region R of the y squared plus z squared, my rho of xyz dv. Well, that means this must be my density function. Rho must be equal to x squared plus y squared. Now, they want me to find my I of z. Well, my I of z is going to be the same integration of r of x squared plus y squared. That's my density function. And then here it's going to be y squared plus x squared dv, because that's the multiplier I need to go around the I of z. So this ends up becoming from 0 to 2 of negative the square root of 4 minus y squared, the positive square root of 4 minus y squared, and then I have this lower bound of 1/2 the square root, no, just 1/2, 1/2 x squared plus y squared, my upper bound of being, the square root of x squared plus y squared, of x squared plus y squared, the quantity squared, and we're going to start out with a dz, and dx, and then dy, because that's what we have up here. Now, I look at this and I think, this looks like a whole lot of fun, but it's going to be much easier if we convert to cylindrical. So if we convert everything to cylindrical, then this is going to be from 0 to pi, and that will be my d theta. And you're thinking, how do I know that? Well, that's based on the fact that my density function is x squared plus y squared. And the fact that I started out from 0 to 2 for my y's. So I'm not doing a full rotation. My x's, so from 0 to 2, I'm not doing a full rotation. And my x's, though, they're doing a half a rotation. So these two combined, these two limits, tell me that I'm really looking at a half a circle, right? So that tells me my theta is from 0 to pi. Well, that makes that a little bit easier. Now I'm going to figure out my r. Well, the circle is based on this equation right here, my r is going to go from 0 to 2. So that's my r. So that's my dr. Now I just have to figure out what z is doing. Well, because remember it's x, it's r, theta, and z. Well, my z, I look at this. This lower bound, because x squared plus y squared is equal to r squared all day long, this lower bound goes from 1/2 r squared. So that's going to be my lower bound, 1/2 r squared. This is my upper bound. This is just r. So this equation is r squared squared. So I have r to the 4th. But don't forget, since I'm in cylindrical, I also need an additional r. So this is why we learned cylindrical, because we took something that was god-awful to something like, ooh, this ain't so bad. Doing our regular integration, we end up with a final answer of 16.7 pi. And that's our final answer when we get done. That's it for this section. So much easier than the last section.